Alright, for this video I'll be working through the Level 2 2015 electricity exam, and I'll be working through question 4. Question 4, circuits. Kahu has two identical lamps marked 6 volts 2 watts. He wants to connect them to a 9 volt battery. He realizes that he will have to connect a resistor to reduce the voltage across the lamps. He connects the circuit shown below. So let's just write some stuff so we can see it. That's 6 volts. I'm just going to forget about the SF because it's at the top. 2 watts, 6 volts, 2 watts, which implies I'll calculate the current each lamp will have when it's operating at its normal brightness. So this, if you buy a box, you have light bulbs at the supermarket, they'll have their voltage rating and their wattage output. So if they're running at their, and the voltage rating is what they should be running at. If you run them too high, they'll blow. If you run them too low, they'll be too dim, and they won't be obviously necessarily what you'd be looking for. So at 6 volts, they'll put out 2 watts of a mixture of light and heat energy, and that's why those, what do you call them, power saver ones are 15 watts, but they can put out equivalent to 60 watt of like light energy, similar to an incandescent. Now I'm just ranting. Right, P, power equals current times the voltage, and that is on your formula sheet right about here. Normal brightness, it's putting out 2 watts, and it'll have 6 volts across it. So I is equal to P over V, which is equal to 6 over... no, take that back. 2 over 6, which is equal to 0.33 amps, because it's just a third. 2SF again, because 2SF the whole way through that we've seen so far. Right, so just before we even continue, and this is a 9 volt battery, this is the positive side, that's the negative side, the large is always positive. There's a law that you'd learn in level 3 called Kerashoff's loop's law, but it's a good way to sort of get intuition, to get a bit of an intuition. If you take any sort of loop that starts at the positive side and ends at the negative side, the sum of the voltages will always equal 0. So that means this is a positive voltage, these use voltages, well, this uses energy. So you can think of it as sort of a negative voltage. So 9 minus something should equal 0. So 9 minus 3 volts minus 6 volts equals 0. So you can take this loop, or you can take this loop down here. Either way, they're 2 closed loops. It's not a bad idea to learn this in level 2, just because it's fairly handy for thinking about sort of solving questions. Right. Calculate the resistance of the resistor that he should use so the lamps are at their normal brightness. So at their normal brightness they need to be at 6 volts, which implies 3 volts is left over for this fella here. So I'll just write the formula that we're probably going to use. V equals IR, and sum of the voltages in a closed loop, CL, is equal to 0. In other words, 12 volts is equal to 6 volts plus the voltage across the resistor, so VR. In other words, simple algebra means that VR is going to be equal to 3. I'm sure you can work that out just by looking at it. 3 volts, yep. Resistance is just the voltage divided by the current. In other words, 3 volts divided by... Ooh, this is tricky, isn't it? We need to write this in. So 0.33 amps. So this is like a... Oh, what do you call this? A trick that would stump, or they'd catch a few students out. You got 0.33 amps going down this one here, and you got 0.33 going down this branch up here. The current splits obviously when it goes from the resistor to these here, so this means the resistor is getting 0.66 amps. So it's just something to be, make sure you don't get caught out on if you're rushing. 66, which means I get 4.5 ohms to SF again. Right, what will happen to the current in the resistor if one lamp blows? So if we look at the circuit, we have 2 paths for the electrons to travel down, which means this lowers the total resistance of the circuit, which means you can get more current flowing out of the battery. If we knock one of these off, it's going to be a series resistance. One bulb's going to end up being in series with this resistor, which means the total resistance to the circuit is going to go up, which means if the resistance goes up, current goes down. voltage will stay the same because it's just the same battery. So it will decrease, so the current will decrease. Losing one bulb means the resistor is now in series with the other bulb, BULB. Comment this increases total resistance of the circuit. Total resistance. I'm not spelling that right. I'm speeding ahead because I'm running out of time. So will decrease total current in the circuit, CIRCUIT. Right, that's that answered. Last question. Kahu sets up a new circuit with different lamps and a resistor as shown in the diagram below. Calculate the voltage across the 4 ohm resistor. So first things first, we're going to need to add these together in parallel. So it's going to be 1 over R total is going to be equal to 1 over R1 plus 1 over R2. You always start with sort of the parallel units, smash them together, make them a series, just make them one component. That's a Thevenin's equivalent. If you don't know, well, if you want to know what this is actually called, you're probably not told it, but it's called a Thevenin, or Thevenin, something else. Thevenin's equivalent, and that's what it's called. So in other words, the total resistance for this sort of little piece is 1 over 6 plus 1 over 3, or 6.0, 1 over 3.0, and that's the same as 3 over 6. So that's is equal to 1 over RT. In other words, RT is equal, so this is just for this loop here, is equal to 6 over 3, and that's equal to 2 ohms. So the total R total for the whole circuit is equal to 2 plus 4, because these are just in series, that's in series with that. 2 plus 4 is equal to 6.0 ohms. Yep, and that's the total resistance for the circuit. And the reason I always do this is if I want to work out the voltage across this resistor, I need to know the current. So I need to know the total resistance for the whole circuit, so I can work out the total current for the whole circuit. So then I can figure out, because the total current is going to be going through him. So then I can work out the current going through him, I've got his resistance, then I'll get the voltage across him. So total current in the circuit, I is V over R, which is 9 volts over, the total resistance is 6 ohms. I should have had that as 2ECF, and that equals 1.5 amps. In other words, V equals IR 1.5 amps times 4 ohms is equal to 6.0 volts across that 4 ohm. 6.0 volts across that 2 ohm resistor. Notice it's in 2SF. So it's always, normally with these questions, you find the total resistance of the circuit, you find the total current. If I wanted to try and find the voltage across one of these resistors, I'd find out the voltage across him first. So if this is 6 volts across this fella, that implies from that law I told you about before, from positive 6 volts, this means 9 minus 6 right here, 3 volts. There's a potential of 3 volts from here to the neutral, well, not the neutral, to the negative. So that means these both get 3 volts. Right, that is that done.